Welcome to the deep dive. Today, we're going to dive into data structures.
Oh, fun.
Yeah, the hidden engines behind every database.
Right.
You know how you can, effortlessly pull up information from, apps and websites?
Yeah.
We'll get ready to uncover the secret sauce that makes it all happen.
It's like a hidden world
Yeah.
of organization.
Right.
Right. Without these specialized structures, databases would be a jumbled mess.
Right.
It'd be nearly impossible to find anything quickly.
So they're specialized filing systems,
Yeah.
each designed for a specific purpose.
Totally.
Some are built for speed,
Yeah.
others for accuracy, and some even excel at handling different types of information.
Yeah.
We have a stack of articles and research here ready to unpack the magic behind hash indexes,
Oh, yeah.
S-stables,
Love those.
B trees, and more.
It's going to be good.
Yeah, and we'll see how these structures are used in popular databases,
Yeah.
like Cassandra and LevelDB.
Yeah.
By the time we're done, you'll be able to impress all your friends
Oh, yeah. Right.
with your newfound data structure knowledge.
Right.
So
Yeah.
let's start with something I think everyone can relate to.
Okay.
Dictionaries.
Oh, yeah.
Remember those?
Back in the day.
Yeah, so hash indexes operate on a very similar principle.
Yeah.
They're all about quick lookups.
Right. So imagine you have a massive list of words
Okay.
and their definitions.
Yeah.
Instead of reading through the entire list,
Oh, yeah.
every time you need to find a word,
Right.
a hash index acts like a direct shortcut.
So it's like having a super fast index at the back of the dictionary.
Exactly. Each word is assigned a unique code or hash,
Mm-hmm.
and this code tells the database exactly where to find the corresponding definition on disk.
Okay.
This direct mapping makes hash indexes incredibly fast,
Okay.
especially for updates.
Okay, let me see if I get this.
Yeah.
Let's say we're tracking views on that adorable cat video that everyone's watching.
Yeah, the one with the...
You know the one?
Yeah.
Every time someone hits play, the hash index quickly updates the view count without having to search through a massive database, right?
Precisely. But what happens
All right.
when your dictionary, or in our case, the data set starts to overflow?
Yeah,
You can't just keep adding pages forever.
right. It's where do you put it all?
That's where things get really clever.
Okay, I'm already intrigued.
Yeah.
So how do hash indexes manage these ever-growing data sets?
They use a technique called segmenting.
Okay.
Think of it like organizing a messy room
Okay.
by dividing it into zones.
Okay.
Hash indexes divide the data log into manageable chunks,
Uh-huh.
making it easier to manage and update.
Okay, so instead of one giant unwieldy file, we have these organized segments.
Right.
That makes sense.
Yeah.
But wouldn't we end up with a lot of duplicate entries
Yeah.
as data gets updated and moved around?
That's where compaction comes in.
Okay.
Periodically, the system merges and cleans up these segments, removing duplicates and ensuring efficient storage.
Okay.
It's like decluttering and reorganizing your digital closet.
That makes sense.
Yeah.
It's like spring cleaning.
Spring cleaning.
Yeah,
For our data.
for data.
But all this talk about data moving around and being updated makes me wonder,
Yeah.
how do hash indexes ensure that we don't lose any data, especially if there's a sudden crash?
Excellent question.
Yeah.
Hash indexes are designed with data integrity in mind.
Okay.
They use techniques like snapshots and checksums to protect against data loss.
So it's like having a backup system in place just in case?
Precisely. Snapshots capture the state of the data
Okay.
at a specific point in time,
Uh-huh.
while checksums act like digital fingerprints,
Okay.
verifying that the data hasn't been corrupted.
So we can rest assured that our data is safe and sound even if something unexpected happens.
Exactly.
That's reassuring.
Yeah.
But I'm also curious,
Yeah.
if hash indexes are so great,
Yeah.
why do we need other types of data structures?
That's a great point. While hash indexes excel at simple key value lookups,
And updates, they have limitations when it comes to more complex queries.
right.
For instance, they're not very efficient for range searches, like finding all users between a certain age range.
Ah, I see. So they're like specialists,
Totally.
really good at what they do, but not necessarily versatile
Yeah,
for every situation.
exactly. And that brings us to our next data structure,
Okay.
SS tables,
Okay.
or sorted string tables.
Mm-hmm.
These tables take a different approach,
Okay.
focusing on efficient storage and retrieval of sorted data.
So if hash indexes are like dictionaries,
Yeah.
what's a good analogy for S-tables?
Imagine a library
Okay.
where all the books are meticulously arranged in alphabetical order.
Okay.
S-tables organize data in a similar way,
Mm-hmm.
sorting key value pairs to make searching and merging data much more efficient.
So instead of having to search through an entire unsorted collection,
Right.
we can go directly to the section where we expect the information to be.
Precisely.
Hmm.
And just like a library might have a directory to guide you, SS tables use an index to quickly locate data within these sorted files.
I'm starting to see how this sorted structure makes a big difference, but wouldn't storing all this information in memory take up a lot of space?
Right.
Especially with massive data sets?
That's a valid concern.
Yeah.
But S tables are designed to be space efficient.
Okay.
They use a sparse in-memory index,
Okay.
which means they only store a few key pointers instead of the entire index.
So it's like having a condensed version of the library directory, just enough information to guide us to the right section without taking up too much space.
That's a great way to put it. And to further save space,
Okay.
SS tables compress data blocks, kind of like packing your suitcase efficiently for a trip.
Clever. So we have these sorted compressed data blocks, all neatly organized.
Yep.
But how does the system actually build and maintain these SS tables? It seems like there's more to the story.
You're right. Incoming data doesn't go directly into SS tables.
Oh.
Instead, it's first written to a temporary structure called a mem table, which resides in memory.
So it's like a staging area where data is collected and sorted before being permanently filed away?
Precisely. Think of it as a buffer zone
Okay.
that absorbs incoming data and prepares it for efficient storage.
Uh-huh.
Once the mem table reaches a certain size,
Okay.
it's flushed to disk as an SS table.
Okay, so it's like a two-step process.
Yeah.
First to the mem table,
Yeah.
then to the S table.
Right.
But what happens if the system crashes before the data in the mem table is written to disk? Wouldn't we lose that information?
That's where the write-ahead log comes in.
Okay.
It acts as a safety net,
Okay.
recording every write operation before it's applied to the mem table or S table.
So it's like a detailed journal
Yeah.
that tracks every transaction, ensuring that no data is lost even in the event of a crash.
Exactly. That's a relief.
Now, SS tables are just one piece of a larger puzzle.
Okay.
They often play a key role within a structure called an LSM tree,
Okay.
which stands for log structured merge tree.
Okay, hold on. LSM trees.
Yeah.
S tables.
Huh.
Starting to sound a bit complicated?
Yeah, you kind of.
Can you break it down for me?
Yeah.
What are LSM trees and why are they important?
LSM trees are a powerful way to organize and manage SS tables.
Okay.
They form the foundation of many popular databases,
Oh, wow.
like LevelDB, RocksDB, Cassandra,
Okay.
and even some search engines.
Wait, did you say search engines?
What?
You mean the technology that powers our web searches is built on similar concepts?
It is. Search engines need to efficiently index vast amounts of text data,
Right.
and LSM trees provide a robust framework for doing just that.
So the next time I'm searching for cat videos,
Yeah.
I can thank LSM trees for making it so quick and easy.
You got it.
But I have another question.
Okay.
How do these systems avoid wasting time searching for data that doesn't exist? It seems like it would be inefficient to check every single SS table for a specific piece of information.
You're absolutely right. That's where Bloom filters come in.
Okay.
Think of them as intelligent gatekeepers.
That can quickly tell you if a particular key is definitely not present in the database.
So they act like a filter, saving the system from unnecessary searches.
Right.
That's pretty smart.
They're a crucial optimization technique,
Yeah.
especially when dealing with large data sets.
Right.
But even with all these optimizations,
Okay.
LSM trees have some trade-offs.
Oh. What are the downsides?
Yeah.
If they're so efficient for searching and storing data, what's the catch?
While LSM trees excel at writes,
Okay.
they can be a bit slower for reads, especially compared to another popular data structure,
Okay.
B trees.
Okay, B trees. I've heard that name before.
Yeah.
They seem to be the workhorses of the database world.
B trees are known for their reliability and efficiency in maintaining data in a sorted order.
Okay.
They excel at both key value lookups and range queries,
Yeah.
making them a popular choice for a wide range of applications.
So if hash indexes are like dictionaries and S tables are like organized libraries,
Right.
what's a good analogy for B trees?
Think of a family tree
Okay.
with its hierarchical structure branching out from a common ancestor.
Okay.
B trees organize data in a similar way, breaking it down into manageable blocks or pages,
Okay.
each containing keys and references to other pages.
So it's a hierarchical structure with each level providing a more detailed view of the data.
Yeah.
That makes sense. But how do B trees ensure that the tree remains balanced,
Right.
and searches stay fast even as data is constantly added and updated.
They have a clever balancing act built in.
Okay.
When a page becomes too full, it splits,
Uh,
ensuring that no single branch becomes too long or unwieldy.
okay.
This maintains a logarithmic search complexity,
Right.
meaning search times remain relatively constant even as the dataset grows.
So it's like regularly pruning a tree to keep it healthy and symmetrical.
Exactly. And just like we saw with LSM trees,
Yeah.
B trees also use a write-ahead log to ensure data integrity.
So they're meticulous record keepers, making sure that every data modification is tracked and accounted for. It's like having a digital audit trail. We'll be back in just a moment to dive into how these two data structure titans, B trees and LSM trees, compare head to head.
I can't wait. Welcome back to the Deep Dive.
Yeah.
Before the break, we were talking about two heavy hitters in the world of data structures, B trees and LSM trees.
Yeah, an epic showdown.
Yeah.
In one corner, we have the reliable and balanced B tree, the champion of consistent reads and transactional integrity.
Right.
And in the other corner, the agile LSM tree, known for its blazing fast write speeds and efficient storage.
Uh-huh.
So how do these titans stack up against each other?
Well, if we're talking about pure write speed,
Okay.
LSM trees generally take the crown.
Okay.
They achieve this by writing data sequentially in compact SS stable files.
That reminds me of like how I pack for a trip.
Oh, yeah.
You know, like I try to fit everything in neatly and efficiently.
Right.
Is that a similar concept here?
It's a great analogy. It's like stacking boxes efficiently in a moving truck
Right.
compared to B trees, which are constantly overwriting data, like rearranging those boxes over and over again.
Okay, so less rearranging means faster write times.
Right.
But what about downsides? There's always a trade-off, right?
Always.
What are the potential drawbacks of using LSM trees?
One thing to consider is the compaction process.
Okay.
While it's essential for merging and cleaning up segments,
Right.
it can sometimes interfere with ongoing reads and writes.
So it's like having road construction on your data highway,
Yeah, exactly.
causing a bit of a slowdown.
Uh-huh. If your application has extremely high write throughput,
Right.
compaction might struggle to keep up,
Okay.
potentially leading to slower read performance
Oh, no.
or even running out of disk space.
So it's like a data traffic jam?
Yeah, like a data traffic jam.
So if LSM trees are all about speed, but with some potential hiccups,
Right.
what makes B trees stand out?
B trees shine in situations where consistency is king.
Okay.
They excel in transactional environments,
Mm-hmm.
ensuring that all data modifications are handled reliably and accurately.
So for tasks like online banking or e-commerce where accuracy is absolutely critical,
Yeah,
B trees would be a better choice.
you got it.
Yeah.
But this consistency comes with a slight performance trade-off.
Okay.
The write-ahead logging and page-splitting operations in B trees
Okay.
can sometimes lead to higher write amplification.
So they're a bit more meticulous in their record keeping,
Yes,
which can add a bit of overhead compared to the streamlined approach of LSM trees.
that's a good way to put it.
Yeah.
Ultimately, the choice between B trees and LSM trees depends on your specific needs.
There's no one-size-fits-all solution.
Nope.
It really boils down to choosing the right tool for the job.
Exactly. Factors like data volume, write frequency, the need for transactional integrity, and read performance requirements
Right.
all come into play when making this decision.
So it sounds like a careful analysis of the specific application
Yeah,
and its data access patterns is essential for choosing the best data structure.
it is.
Okay, so we've explored hash indexes, SS tables, LSM trees, and B trees.
That's a lot.
What a lineup. Are there any other data structures we should know about?
You bet. There's a whole world of specialized indexing structures out there,
Really?
each designed for specific use cases.
Hmm.
Let's explore a few more intriguing examples.
Okay, I'm ready to expand my data structure vocabulary. What else is out there?
Let's talk about clustered indexes.
Okay.
Unlike their non-clustered counterparts, which simply point to data locations,
Right.
clustered indexes store the actual data within the index itself.
So it's like having a self-contained travel guide that includes both maps and detailed information,
Yeah,
eliminating the need to consult separate sources.
that's a great analogy.
Yeah.
This co-location of data and index can significantly speed up read performance for certain queries.
Oh, wow.
Then we have multi-column indexes,
Okay.
which combine multiple fields to allow for more complex search criteria.
I see. So if we're searching for restaurants in a specific area on a map,
Yeah.
a multi-column index could combine location data with other criteria like cuisine type or price range.
Exactly. They add more dimensions to your search capabilities.
I like it.
And if you're dealing with location data specifically,
Okay.
R trees are your best friend.
Yep.
They're designed to handle multi-dimensional data, particularly geospatial information.
So our trees would be used in applications like mapping services, GPS navigation, or even finding the nearest coffee shop.
Precisely. And let's not forget about full-text search and fuzzy indexes.
Oh, yeah.
They allow you to search for words even with typos, variations in spelling, or synonyms.
It's like those helpful search engine suggestions and autocorrections that save us from our own spelling mistakes.
You got it. They make searching for information more forgiving and intuitive.
All these data structures are amazing. But with all this talk about disks and storage optimization, I can't help but wonder, is there a future where we can just keep everything in memory for lightning-fast access?
That's a great question. And it leads us to the world of in-memory databases.
Ooh, in-memory databases.
As RAM becomes more affordable and technologies advance, storing entire data sets in memory is becoming a reality.
So it's like having a super fast brain that can access information instantly without the delays of reading from a disk.
Precisely.
Yeah.
In-memory databases offer incredible performance gains, especially for read-heavy applications.
Wow. But what about data durability? If the power goes out, wouldn't we lose everything?
That's a valid concern, but in-memory databases have several tricks up their sleeves to address this.
Okay.
Techniques like battery backups, write-ahead, logs, snapshots, and replication.
Wow, that's a lot.
Ensure that data is protected, even if there's a power outage or system failure.
So it's like having a backup generator for your data.
Exactly. And it's not just about durability.
Okay.
In-memory databases are also pushing the boundaries of capacity.
Oh, wow.
We're seeing innovative approaches like anti-caching that allow these databases to handle data sets larger than available memory.
Anti-caching? That sounds kind of counterintuitive. How does that even work?
It's a clever way of managing which data is kept in memory and which is temporarily offloaded, ensuring optimal performance, even for massive data sets.
So it's like having a mental filing system that prioritizes the most important information while keeping the rest readily accessible when needed?
Precisely. In-memory databases are constantly evolving, pushing the limits of what's possible in data management. But let's shift gears a bit and explore how these data structures are applied in different database use cases.
Okay, I'm ready for a change of pace. What other fascinating aspects of the data world are we going to uncover?
Let's dive into the distinction between transaction processing and analytics.
Okay.
These two areas have contrasting demands and rely on different data management approaches. Have you ever wondered how websites can handle millions of transactions simultaneously?
Yeah.
Like processing orders or updating accounts, while also providing insights from vast amounts of data.
It does seem like those are two very different tasks, each requiring a specific approach.
You're absolutely right. We call these two areas OLTP and OLEP. OLTP stands for Online Transaction Processing.
Okay.
And it's all about handling a constant stream of individual transactions.
So it's the engine behind those real-time interactions we have online, like adding items to a shopping cart or transferring money between accounts. Speed and reliability are paramount in these systems.
Exactly. Now, OLAP stands for Online Analytical Processing.
Okay.
And it's more about analyzing large data sets to uncover patterns, trends, and insights. Think of it like digging deep into data to answer business questions, predict future outcomes, or understand customer behavior.
So OLTP is for real-time actions, while OLAP is for taking a step back and analyzing the big picture. It's like the difference between sprinting and running a marathon.
That's a great analogy. They require different approaches to data management, with OLTP systems prioritizing speed and concurrency for individual transactions.
Okay.
While OLP systems focus on efficient data aggregation and complex queries for analytical insights.
That makes sense. It's like having different tools for different jobs.
Yeah.
But if analytical processing requires a different approach, how is data typically managed for these types of tasks? I've heard the term data warehousing thrown around. What does that mean exactly?
Data warehousing is a key concept in the world of analytics.
Okay.
It involves collecting data from various sources, cleaning it up, and organizing it in a way that makes it easy to analyze.
So it's like building a specialized library dedicated to housing and organizing data specifically for analysis.
Exactly.
That way the performance of transactional systems isn't impacted by these complex analytical queries.
Exactly. And within this data warehouse, we often use specialized schemas to organize the data for efficient analysis. Two common approaches are star schemas and snowflake schemas.
Okay, I've heard those terms before, but they sound a bit intimidating. Can you break them down for me?
Absolutely. Imagine a solar system with the sun at the center.
Okay.
And planets orbiting around it.
Okay.
In a star schema, the central sun is the fact table, containing the core data about events.
So if we're analyzing customer purchase data, the fact table would store information about each purchase, like the items bought, the date, the amount spent, and so on.
You got it. And the planets orbiting around this fact table are the dimension tables.
Oh.
They provide context about these events.
So the dimension tables would contain details about the customers, the products they purchased, the time of the purchase, and other relevant information.
Precisely. This structure makes it easy to slice and dice the data, exploring different aspects of the information and answering complex questions.
I'm starting to see how star schemas make data analysis more intuitive. But what about snowflake schemas? How do they differ?
Snowflake schemas are essentially an extension of star schemas,
Okay.
where dimensions are further broken down into subdimensions.
Okay.
Think of it as adding moons orbiting around the planets in our solar system analogy.
So instead of having a single customer dimension, we might have subdimensions for demographics, location, purchase history, and so on.
Exactly. This normalization can sometimes improve query performance and lead to more efficient storage,
Right.
but it can also add complexity.
Yeah.
The choice between star and snowflake schemas depends on the specific analytical needs and the trade-off between simplicity and performance.
It seems like there are a lot of factors to consider when designing a data warehouse for analytical processing.
There are.
But what about the actual storage of the data itself? Is there a way to optimize that for analytical queries?
You're thinking along the right lines. That's where column-oriented storage comes in.
Ooh, column-oriented storage.
It's a fundamentally different way of organizing data that's tailor-made for analytical workloads.
Okay, I'm intrigued. How does column-oriented storage differ from the traditional row-based approach?
Imagine a spreadsheet.
Okay.
In a traditional row-oriented database, data is stored row by row, just like in a spreadsheet.
Right.
However, in column-oriented storage, all the values from each column are stored together.
So instead of reading an entire row to access a specific piece of information, column-oriented storage allows us to read only the data we need.
Exactly. This is incredibly efficient for analytical queries that often involve aggregating or filtering data based on specific columns. It's like having a library organized by subject instead of by author.
Great.
If you want to read about data structures, you can go straight to the data structure section and find all the relevant books grouped together.
That's a brilliant analogy. It makes perfect sense. So by only reading the necessary columns, column-oriented storage reduces the amount of data that needs to be processed,
Right.
leading to faster query times.
Precisely. And there are additional optimizations like column compression
Oh, wow.
that further enhance storage efficiency and performance.
So it's like packing similar items together in your suitcase to save space.
Exactly. Column compression exploits the repetitive nature of data within columns to significantly reduce storage space and improve query performance.
It's a win-win. But column-oriented storage sounds like it's primarily optimized for reading data?
Right.
What about writing data? Is that a challenge with this approach?
Writing to column-oriented storage can be more complex than reading. But techniques like LSM trees, which we discussed earlier, can be effectively employed to handle these write operations efficiently.
It's amazing how these different data structures and techniques can be combined to create powerful solutions. We'll be back in just a moment to explore even more ways to turbocharge analytical queries and wrap up our deep dive into the world of data structures.
Welcome back to the deep dive. We've been on quite a journey exploring the intricate world of data structures, from like those fundamental building blocks like hash indexes to the specialized powerhouses like column-oriented storage.
It is fascinating how these structures, often hidden from view, play such a critical role in shaping our digital experiences.
Before we wrap up our exploration, I'm curious about ways to further enhance analytical processing. We touched upon column-oriented storage, but are there other techniques that can really turbocharge these types of queries?
Absolutely. One powerful approach is to use pre-computed results. Think of it like having a cheat sheet.
Oh, okay.
With instant answers to frequently asked questions. Okay, I like the sound of that. But how does that actually work in a database context?
We can use techniques like data cubes and materialized views.
Okay.
These are essentially pre-calculated summaries or aggregations of data that are stored separately.
So instead of performing complex calculations every time a query is run,
Right.
the system can simply retrieve the pre-computed results. That sounds incredibly efficient.
Exactly. It's like having a shortcut that bypasses the heavy lifting, making analytical queries lightning fast. But it's important to note that these pre-computed results need to be updated periodically to reflect changes in the underlying data.
That makes sense. It's like keeping your cheat sheet up to date so the answers are always accurate. Wow, we've covered so much ground in this deep dive. From basic concepts to advanced techniques, it feels like we've truly uncovered the hidden world of data structures.
It's been quite a journey, hasn't it? We've explored how these structures enable efficient storage retrieval and analysis of the massive amounts of data that power our world.
I have to say, I'm feeling a bit overwhelmed, but in a good way. It's incredible to realize how much thought and ingenuity goes into designing these systems.
And the field is constantly evolving. New challenges emerge as data volume grows and analytical demands become more complex.
It's both daunting and exciting. So for our listeners who are eager to learn more, what resources would you recommend? Where can they go to continue this exploration?
There are a wealth of resources available. For a solid foundation, classic textbooks like Database System Concepts and Designing Data-Intensive Applications are excellent starting points.
Those sound like great foundational reads. What about online resources? Are there any websites or courses you'd recommend?
Absolutely. Websites like Hacker News and Stack Overflow are great for staying up to date on industry trends and engaging in discussions with fellow data enthusiasts. And for online courses, platforms like Coursera and Udemy offer a wide range of options, from introductory to advanced levels.
It sounds like there's something for everyone, regardless of their technical background. What other avenues would you suggest for gaining practical experience in this field?
Contributing to open source projects is an amazing way to gain hands-on experience and learn from some of the brightest minds in the industry. Projects like Apache Cassandra or LevelDB offer opportunities to dive into the code and contribute to real-world solutions.
That's a fantastic idea. It's like a digital apprenticeship, learning by doing and making a real impact. As we wrap up our deep dive, I want to ask you, what's the one key takeaway you hope our listeners will remember from this episode?
The world of data structures and databases might seem complex, but at its core, it's all about solving problems and enabling innovation. By understanding the fundamental principles and the various techniques we've explored, anyone can unlock the power of data and make a real difference in the world.
So it's not just about memorizing algorithms or mastering specific technologies. It's about understanding the core concepts and applying them creatively to solve real-world challenges.
Exactly. And as data continues to shape our world, the ability to understand and manage it effectively will only become more valuable.
Well said. On that note, I want to thank our listeners for joining us on this incredible journey into the world of data structures. We hope you've enjoyed this deep dive and that it sparked your curiosity to learn more.
Until next time. Keep exploring, keep learning, and keep pushing the boundaries of what's possible with data.
And remember, the power of data is within your grasp, so go forth and data wisely, my friends.